All right, so the practice test. Let's see. We don't have enough time probably to go through every question on here in any kind of detail. But what I want to do is entertain any questions you have, specific questions about these problems. Okay. So what questions do you have about any of these questions on the test itself? Hands, please. Don't just shout out. Okay. Jessica.
Can you tell me what 13?
The proper formula to find the molar density of a gas at STP. This is on your, well, it is in your unit handout, but it is also on your test references. Okay? The proper formula for finding the molar density of a gas at STP is this calculation right here. James, you think you might need to know this for the test tomorrow?
Monday?
Yes. So I'm sorry. Yes, you're right. Monday. We're not going to be here tomorrow. Tomorrow's Saturday. Okay. You going to be here? Okay. So molar density of a gas, as long as you're at standard temperature and pressure, is a real simple calculation, in the sense that you can put the molar weight. That you have to calculate the molar mass to find the molar. That's the molar mass. Remember how to calculate molar mass? We did it for a month, right? And divide it by the molar volume. And molar volume is always the same. This is from your mole day project. Okay, molar volume is 22.4 liters of a gas. Okay? So you need to know, there's something that you need to know, that for any gas, this is, you should have known this, and from the time you did your mole day project, any gas at standard temperature and pressure, we symbolize that STP. Standard temperature and pressure is 1 atmosphere and 0 degrees C. That's standard temperature and pressure. So any gas at standard temperature and pressure has a molar volume. That means that 1 mole of that gas, X, whatever that gas is, 1 mole of that gas is equal to 22.4 liters of that gas. Okay? Which we can write in a fraction if we need to make it work out. 22.4 liters of gas X over 1 mole. That's also a way of writing molar volume. Okay? And this is what we call molar volume. Okay? Make sense? Molar, anything usually means how much there is at 1 mole. How much in that measurement unit there are in 1 mole. So molar mass is the mass, the number of grams, if you will, of a substance if there's 1 mole of that substance. Okay? Does that make sense? All right. That was number 13 was the question. So what next question do you have for me today? 19? All the gas laws that we study in this unit are based on, come on, you guys know this. Kinetic molecular theory. Kinetic molecular theory. Oh, yeah. Yeah. Kinetic molecular theory of gases. Right. I'm saying, go away, don't come, I don't want you here. I'm kidding, I'm just joking. What? All right. All right, let's see. What's the next? What do you have next? What do you want? What conversions would be used to convert from the volume of one gas to the volume of another in a chemical reaction when the gases are at standard temperature and pressure? Well, let's see. So I've got the volume of a gas. Now, I'm just making up a volume. Please don't ask me 5 minutes or 10 minutes from now, where'd you get that volume from? What am I doing? Making it up. All right, I'm going to just say I've got 5 liters of this gas. Well, let's see. Let's get a specific gas. How about nitrogen gas, okay? All right, 5 liters of nitrogen gas. What I want to do is to go from what the problem is asking me. This is what number was this again? 19.
No, that's not 19.
No, that's not 19. You're right. Was it 12? Okay, what conversions do I need? Well, to get from, if the gas is at STP, then this molar volume is the first one I need. Here's an equality statement that fits this. Everybody looking? Everybody paying attention?
Yeah.
Here's an equality statement. Tylen, you looking over here? Don't look like you're looking. Pay attention. This is an equality statement for molar volume.
Please pull it down.
Here's an equality statement for molar volume. Okay? Right here. 1 mole of any gas is equal to 22.4 liters of that gas at STP. And the question for number 12 is saying that they are at standard temperature and pressure. So I can convert from liters to moles using that ratio right there. 22.4 liters of N2 equals 1 mole. So there's one conversion I need. Okay? So those cancel, right? Now to get from moles of one thing to moles of another, and it says we're going to go from the volume of one gas to in a chemical reaction, you got to have a chemical reaction. You got to have a chemical equation to describe the reaction. And they come up with a molar ratio. So let's build a chemical reaction for this. I'm just making this up in order to show you where you get these conversions from. Okay? So let's react N2 with H2. Those are gases. And it even makes a gaseous product, NH3. So all these are gases. I need to write the physical states. Review. Okay? And I need to balance the equation. What do we use for balancing equations?
AI.
An AI chart, an atom inventory chart. Can I skip that? Is that okay if I skip it today, just to make it faster? You have to write an atom inventory if it's required, but I'm going to skip it just for now. Okay? All right. So to make this work out, I need 2 of those and 3 of those. Okay? All right. So I can get a molar ratio once I've got a balanced equation. That's another conversion that I need. So let's see. I've got moles of N2. I need 1 mole of N2 on the bottom. If I've got moles of N2 on the top here, I've got to put moles of N2 on the bottom here, and the number I need is this coefficient, implied coefficient of 1. 1 mole of N2. All right? So I'm going to give you a choice. You can tell me, do I want to calculate the amount of H2 or the amount of NH3? I hear both. Okay. H2, raise your hand. NH3, raise your hand. Oh, NH3 wins. All right. So I'm going to calculate the NH3. How many moles of that do I have? 2 moles of NH3. Okay, that allows me to cancel my units of measurement and the species. Okay, and there's another conversion that I need. The question is asking, what conversions do you need? I need a molar volume. I need a mole ratio. Molar volume, mole ratio. Okay? All right, finally, if I'm going to get the volume of NH3, I need a conversion unit, so I need an equality statement. Well, there's the equality statement again. 1 mole of the gas, so I can put 1 mole then of NH3. What am I going to put on the top? Yeah, that's the other side of the equality statement. That's what I need, 22.4 liters of NH3. Okay? Cancel units, cancel species. And the question says if I want to go from volume of one gas to volume of another, what do I use? Well, I'm at the volume of the other gas. So I need molar volume. I need a molar ratio. I need molar volume again. Okay? Okay, so you need molar volume. Molar ratio, we've needed that ever since we were doing stoichiometry. I always need a molar ratio anytime you're doing a chemical reaction, going from one species to another. And this is just molar volume again. Notice the numerical values are just flipped here. This one and this one look the same. I got a different species, but the numbers are flipped. Does that make sense? Numbers and units of measurement are flipped. Okay? And if I do the math, I'm going to have the volume of the other gas, and it turns out to be 10 liters of NH3 when I do the math. Got it? Okay, so stoichiometry with gases, really, really simple. I got molar volume. Don't have to do any calculations for molar mass. Simple stuff. Next question. Say what now? I don't know. Let's do that math and find out. So this was number 12. Let's see. All right. Let's do number 27 then. Flexible container has an initial volume. Well, I know that must be V then, huh? Yeah, it means the container will expand and contract. Okay, and you have to have that if you're going to do if you're going to be changing the volume of the gas. Say what? No, probably not. Not the way I taught you to do it. Okay. All right, let's see. A volume of 2.50 liters. And we have a temperature of 21.5 degrees C. T equals 21.5 degrees C. So the first thing you're always doing when you're doing gas law calculations is write down your knowns and unknowns. And it's got a pressure of 1.2 atmospheres. Pressure equals 1.2 atmospheres. Okay, let's see here. 27. The temperature increases. So I got a new temperature. That must be temperature 2. So this is temperature 1. Temperature 2 is 35.7 degrees C. Pressure, new pressure, 90 atm. So pressure, this must be pressure 2, and this is pressure 1 then. Is it 90 or 0.90? Let's see where it's 0.90. 0.90 atm. Okay. And then what's the volume? So that must be V2 because I've already got a V over here. We don't know what that is. It's asking what it is. And so I've got all of these variables. I go to the list of my test references of all the gas laws and find the one that has V1, T1, P1, V2, T2, P2, and that's this equation, right? This gas law right here, this equation, called the combined gas law. All right? So I can put down this gas law, and it's V1, P1 over T1 equals V2, P2 over T2. All right. Before I go too far, I can't use temperatures in degrees C. I have to convert temperatures to Kelvin. So we got to take 21.5 degrees C and add 273.15 to that, and I get 294.65 K. But going back to the very beginning of the semester in Unit 1, we learned how to do significant digits, how to figure out significant digits. There's an empty slot there, meaning that this 5 that results from that column is going to be rounded off. And we use an arrow to show rounding off. So this is now 294. And the 5 makes the 6 round up to a 7, 294.7 K. And that's what we need for this temperature is 294.7 K. Alright? And this temperature has to be changed as well. Should have left a little more room over here, I guess. 35.7 degrees C. 273.15. Okay, 5, 8, 8, this is 10, so 308.85. Got an empty slot again here, Dick. Forrest. Yeah. Richard, sit up. That's K. Got an empty slot there, so that 5 that results is going to be underlined. And I need to round off this number then to the correct number of significant digits that results, 308.9 K. And so that's what this becomes here, 308.9 K. Alright? So now we're ready to plug everything in. I'm going to be looking for V2 here. Let's plug in the numbers we have. 2.50 liters is our V1. Multiply that times P1, that's 1.2 atmospheres. And the temperature we're going to put on the bottom here is 294.7 K. Over on the other side, V2 we don't know, so we're going to leave that alone. We're only plugging in the known values that we have. We're not plugging in anything else. We do have a known value for the pressure. This time 0.90 atmospheres. And we do have a known value for the temperature here. That's 308.9 K. Okay, now we can do some math to try and get the unknown all by itself. So we need to be able to get rid of this number and this number. And the way we do that is multiplying by the reciprocal of those. So this goes on the top, 308.9 K. This one goes on the bottom, 0.90 atmospheres. And because I have this number exactly the same as this number, top and bottom of two fractions in a multiplication problem, these can cancel. And these numbers, I have this number on the top and this one on the bottom of a multiplication problem where they're in fractions. Those numbers can cancel. Likewise, the units can cancel, K on top, K on bottom, and atmospheres top and bottom. So I have V2 by itself. But whatever I do to this side of the equation, I must do to this side. So I've got to take this same fraction and multiply this over on this side. Okay? So 308.9 K over 0.90 atmospheres. Okay? All right, I've set it up now. So it looks like that the K's are going to cancel. I got those on the top and bottom. Atmospheres are going to cancel their top and bottom. The only measurement unit that's left is liters. And because liters is a measurement unit that measures the dimension of volume, I know I've probably set this up right. At least at this level in chemistry, that's as far as we're going to go in here. So we set it up right. It's called dimensional analysis. So now we're ready to do the math. I want to figure out how many liters of gas we actually have here. Okay? All right, let's move my there just a little bit so we can see better. 308.9 times 2.50 times 1.2. Now I'm going to hit my enter button and then separately do divide. Divide by 0.90 and hit my enter button again, and then divide again by 294.7 and hit enter, and that's going to give me the unrounded answer that I need. So 3.493948648. Units I have left up here are liters, and that equals V2. But now I need to round off. So I'm going to look at all of these measurements in the problem. Remember, we're only going to look for measured or calculated numbers when we're figuring out significant digits for the answer. And this number has the least number of significant digits. I've got 2 significant digits here. This has 3, and this has 4, 2 here. So the least digits are found in these 2 numbers. Remember, leading zeros are not significant, so only these 2 digits are significant here. So I want 2 digits in my final answer. I'm going to underline everything after these first 2 digits. And we're going to write a final answer. We're going to use an arrow to show we're rounding off. 3 point, what's that going to become? 5 liters equals V2. And that's the end of the solution, so I'm putting a period there, okay? All right, so is that the answer you got, Reese? Good? All right, so just a reminder, kind of review. The way we solve all these problems is the same. The way we solve all these gas law problems, FDR, Forrest, Dick, Richard. The way we solve all these gas law problems, the way we solve all these gas problems is the same basic process. First thing you do is list all your knowns and unknowns. Now, kind of an aside or sub part of that is you got to make sure your temperature's in Kelvin. Okay? After you write all your knowns and unknowns, then you write down the equation that fits those. Then you go to plugging in the values that you know. Plugging in the values you know. So you get this part. Then you're going to isolate the unknown, and you do that by multiplying by something that's going to get rid of everything on this side except for your unknown. And you do the same thing. What you do to this side, you have to do to this side. So this is called isolating the unknown, this step right here. So you plug in the values first, then isolate the unknown. Then you're ready to solve you do your cancellation, and then you're ready to solve the problem. Okay? Yes. Yes, you can go to the restroom. All right?